At the end of last class, we were talking about F-test, or what we call global test of model utility, which means instead of testing each parameter, each individual independent variable, we test the entire model and try to find out whether this entire model is useful for the purpose of predicting the value of the dependent variable, right? So we use this example of pizza sale, I believe, or pie sale, okay, as the dependent variable, and we use the price and advertising as independent variables, okay? And, based on this F statistic and the p-value, what can you say? Is the model useful? Yep. Well, if you want to use a critical value approach, you won't be able to say that immediately, because you have to go to the F table and find the critical value and compare this F statistic to the critical value, right? And if on any particular F distribution for certain alpha value, let's say 0.05, and with certain degrees of freedom here, this F distribution has different shape depending on the degrees of freedom, right? And I told you F statistic has 2 degrees of freedom, because F statistic is variance divided by variance, okay, comparing 2 variances, okay? So typical F statistic has F alpha, okay, numerator degrees of freedom and denominator degrees of freedom, okay? And numerator degrees of freedom is k and n minus k minus 1, right? So remember that. So you have to go to the F table and look for this critical F, which has 0.05 on its outside. That's the rejection region, okay? And then you see where your test statistic falls, okay? In case your test statistic falls here, right? Your test statistic, which is F statistic, right? Then you can reject the null hypothesis. If the test statistic is less than the critical value, then you won't be able to reject the null hypothesis, right? You know, the similar concept, the same idea with the t-test that we've been dealing with, right? But by looking at the p-value, you can immediately make the conclusion, right? What's the p-value in this test? .012, right? Okay, so what is your conclusion? Reject the null hypothesis, okay? Because apparently the test statistic 6.5386, right? If this is 6.538 whatever, right? Then the area outside the test statistic, which is p-value, okay, that is only 0.012, right? You know, this white shaded area, rejection region, that has the area size of 0.05, right? But the red shaded area, which is the p-value, is less than 0.05. Which means your test statistic is greater than the critical value, right? Okay? So it's, you know, clearly, obviously, you can reject the null hypothesis, okay? If you use alpha level of 0.05, right? If you want to use alpha level of 0.03, what will be your conclusion? still reject because p is less than alpha, right? Well, if you want to use critical value approach, you might have some problem because if you look for F table in your textbook or on the internet, do search for F table, I don't think you can find F table for alpha value of 0.03, right? You can probably find a F table for alpha value of 0.01, 0.05, 0.1, or maybe 0.025, right? But I don't think you can find any, F table for alpha value of 0.03, right? So, that's the advantage of using p-value approach, right? You don't need to find critical value, right? You just need to make the conclusion right, or you can make the conclusion right away if you use p-value approach, right? Well, what if you use alpha value of 0.02? In other words, you want to be 98% confident in your conclusion, right? What would be your conclusion? Still reject? Okay. How about 0.01? Yeah, then you won't be able to reject because p is not less than alpha value, right? Okay, so, it's pretty much the same idea as before. As long as you understand that the p-value approach concept, you can easily and quickly make the conclusion by looking at this printout, okay? All right, so that was the idea. Did I start? Yeah, okay. It's recording, right? Okay, yeah. So that was the idea of the global test of model utility. Today, we're going to talk about slightly different concept. We're still talking about F-test, right? But it's called the portions test of using the portions test about the model, okay? In other words, instead of global test, global meaning we're testing entire model, right? We're going to test part or portion of the model, right? So, and see whether this, we're talking about if you have 5 independent variables in your model. Independent variable so far we've been just using the term independent variable, right? But if you look at the researches and higher level econometrics textbooks, right? Many times we use explanatory variable, okay? Because those are the variables that explain the variability in the dependent variable, right? In other words, in pie sales, okay? We're assuming price and advertisements, right? Those two variables explain what happens in pie sales, okay? Or many times we use regressors. Excuse me. Regressors or independent variable. Well, if you type this word in your word processing software like Word, right? You're going to see red underline here, okay? Because apparently there is no such word in the English dictionary. Okay? So you will see this underline. But this is the word we use in econometrics, regressor, okay? As opposed to regress C. Regress C. Okay? Regress, I think 2 E's, because it's hardly, grammatically I think 2 E's are correct, okay? But we hardly use this word, okay, for some reason, okay? Regress C refers to the dependent variable, right? Regressor refers to independent variable. And, in reality, we use regressors a lot, but we never use regress C. Okay? Anyway, so independent variable, explanatory variable, regressors are the same thing. Okay? So here we have a few variables we consider as explanatory variables. Okay? Then sometimes we wonder, we have these 5 independent variables. Okay? And in the presence of the other 4, is the last independent variable really important? Does that make really significant difference in predicting power of this model? In other words, does it improve this model? Right? That's the question we want to ask here. Right? So here, the null hypothesis says variable xj, I believe it's xj, yeah, xj, does not significantly improve the model after all other variables are included. Right? If you put it differently, in the presence of all other variables, that one particular variable xj is useless. Right? That's what the null hypothesis claims. You remember the null hypothesis for the global test of model utility? Right? Null hypothesis says beta 1 equals beta 2 equals beta 3 equals ... beta k equals or 0, right? Which means your entire model is useless, right? All right, the same idea, right? So here null hypothesis claims that one particular variable xj doesn't help. It's not useful, right? Alternative hypothesis says variable xj is useful. In other words, it significantly improves the model after all other variables are included. Okay? All right. Test statistic is F statistic. Again, F statistic is the ratio of 2 variances. Okay? Well, here, how do you calculate this conditional SSR? From the SSR for the entire model, first you include everything and run the regression and see sum of square for regression. And then second time, so you have to run regression twice in order to calculate this. Second time, you eliminate that particular variable xj, right? And then run the regression without xj, right? And calculate SSR, right? And notice the difference between the sum of square for regression with the entire model, right? And the sum of square regression without that one particular variable, right? And then we divide it by MSE, right? So this numerator here, right? The difference between SSRR and SSRR except J, that's the conditional SSR, right? The SSR for xj given that all variables are included except for j, right? Well, the degrees of freedom for numerator is 1 because we're dealing with one particular x variable, xj, right? But the degrees of freedom for denominator is typical degrees of freedom for error, n minus k minus 1. Okay? All right? And here, again, we're explaining that conditional sum of squares, right? How do you calculate this sum of square? x1 given x2. Well, I guess we're talking about 2 independent variables. So in this example, we have 2 independent variables, x1 and x2. Okay? And we're trying to calculate the sum of square for regression due to x1, given that x2 is already included. Right? So we have 2 independent variables. Okay? And first time you run the regression with the entire model, x1 and x2. Right? Second time, you delete or drop x1, right? And just run the regression with x2 only, and notice SSR, right? And the difference between those two sum of square for regression, okay, that's the conditional sum of square for regression for x1 given x2. Okay, is it clear? Okay, all right. So that conditional sum of square measures the contribution of x1 in explaining the total variation, right? Net of the effect of x2. Okay, so x2 variable explains some portion of the variability in y variable, right? But in addition to or on top of that, above and beyond that amount of explanatory power of x2, just how much additional explanatory power does x1 add, right? That's what we're talking about. Yeah? Okay. So going back to that pie sales example, okay, and we want to see what the significance of price, right? When we already considered advertisement, okay? So in the presence of advertisement as the explanatory variable, right, in this model, when we add another variable, price, does it really make any significant difference, right? In other words, does it significantly improve the model in predicting the pie sales? Okay? Well, for that, let's say alpha level of 0.05, degrees of freedom will be 1 and 12, right? Because we are, again, the degrees of freedom for numerator, we're talking about just one particular variable price, okay? So that's 1 and 12. So if you go to the F table and look for critical value, you're going to have 4.75. Okay? Just in case, let me show you how to use F table once again. What was it? F table, okay. Okay, so this is entire table is for alpha value of 0.05, right? And we are looking for degrees of freedom 1 and 12, okay? So here, if you look at this, this W is supposed to be df1, df2, right? Supposed to be this way, but somehow this one shows up as W in this computer, right? So these numbers are degrees of freedom 1. In other words, that's the numerator degrees of freedom. These numbers, this is the numerator degrees of freedom. This is the denominator degrees of freedom. Okay? So 1 and 12 right here, right? 4.75. That's how they came up with the critical value for the F statistic, right? Okay. All right. And then we ran the regression. First time with the both variable, second time with x2 only, right? And sum of square for regression here is 29,460, right? And second time without x2, without x1, right? Came out to be 17,484, right? So sum of square for x1 given x2 is sum of square for regression from the full model minus sum of square for regression without that particular variable, right? And that divided by sum of a mean square error here, 2252, 7.77, right? And we come up with, that comes up with 4.316. Okay? So test statistic exceeds the critical value, right? And you can reject the null hypothesis. This null hypothesis. Null hypothesis says price does not improve the model when X2 advertising is included. Okay? But you have rejected that null hypothesis. So what is your interpretation? What does that mean? X1, or including the price in your model, significantly improves the predictive power of your model. Okay? Yeah, for this test, unfortunately, we cannot use p-value. We have to use critical value approach. Okay? So you will need an F table for this test. Okay? All right? Here's another related concept. It says relationship between test statistics, particularly t-test and f-test. Okay? And this is actually the reason why I told you to omit one section from chapter 13, right? In chapter 13, there was a section regarding f-test on beta parameter, right? All right. Yeah, well, in chapter 1, we had only one independent variable, right? So beta 1 equals 0, beta 1 not equal to 0, right? To test this hypothesis, we use the t-test, right? But after that, the textbook also had f-test, how to use f-test for this test, right? And I told you to just completely disregard it because it's useless. Okay? And here's the reason, actually. Okay? So partial F statistic developed in this section that both used to determine the contribution of independent variable to a multiple regression model. Okay? The hypothesis test associated with these two statistics always result in the same decision. Okay? What are we talking about? Look at this output. Okay? And when you ran the regression with both independent variables, price and advertisement, okay? Here, look at the p-value for the price. Okay? Well, of course, we get the negative coefficient here, and as a result, we get negative test statistic. Why? What does that tell us when we get negative coefficient? Huh? Yeah, go ahead. Yeah, it's downward sloping, right? Which means what? Ma, you know that, right? Negative relationship between price and pie sales, which is what? Expected, right? Expected, right? You know the relationship of the demand curve, right? When you raise the price, quantity demanded goes down, right? Okay, that's the idea. So it's pretty much expected, normal result, right? And the p-value comes out to be 0.039, so it's about 0.04, right? So if you use 0.05 as alpha level in two-tailed test, right? What is your conclusion? Yeah, you can reject the null hypothesis, and your conclusion, your interpretation will be price is an important variable, right? Or price makes significant difference in your in predicting the pie sales, right? Yeah. Well, there's the t statistic of negative 2.3056 here, and if you square it, you get 5.316. Okay? And that 5.316 was here. 5.316, right? That's the F statistic you will get if you test the significance of that one particular variable, price, right, using the portions test. So try to understand what's happening here, right? In this F test, we have this pi sales as beta naught plus beta 1 price plus beta 2 advertisement. Okay. First time we ran the F test, so we thought about including both independent variables versus including only advertisement and dropping the price variable, right? And we ran the F test, and as a result, we got that test statistic of 5.316, right? And that was, okay. Test statistic F.05, 112, that was 5.316. Okay? Second time, you can just use the normal testing, right? T-test, right? So just run the test on beta 1 using this hypothesis testing, right? And you do that, and you got the test statistic of negative 2.3, test statistic of T 0.05 degrees of freedom 1. Okay. Oh, I'm sorry. The degrees of freedom 12. Okay. That came out to be negative 2.3056, right? 057, whatever, right? And we found out, well, your conclusion will be the same, right? Whether you run this F test or this T test, yeah, you will come to the same conclusion. Look at the p-value here, 0.03979, right? And if you find the p-value from this test, unfortunately we don't have that p-value here, right? But you will get the same. If you use the computer to calculate the p-value, you will get the same p-value, right? So this is what we're talking about here. If you're talking about the same degrees of freedom, 12 for the test statistic, T statistic, and 12 for the denominator on F test statistic, with the 1 as the numerator degrees of freedom for F statistic, right? We always get, if you square, this is the F statistic, right? And your conclusion will be the same, because p-value for this will be the same as p-value for this test statistic. Okay? Well, think about it. In chapter 13, we were dealing with the simple linear regression, right? So we had y equals beta plus beta 1 x1 x. That's it. That was it, right? And normally we just use t-test to see this. Well, once you estimate, right? We test this estimated parameter, right? See whether it's significant or not, right? Well, since we have only one independent variable, if that independent variable makes significant difference in the predicting y, then obviously the entire model is useful, right? Okay, once again, right? This entire model has only one independent variable. So if that independent variable is useful, then entire model should be useful, vice versa, right? If that's not useful, then entire model should be useless. In other words, running the t-test on one independent variable should be the same thing as the running the F-test for entire model if you're dealing with one independent variable, right? Here, same idea, right? We have two independent variables, right? If you are testing the significance of price here using the t-test, or if you use the portions test to see whether price makes any significant difference in the presence of advertising, you're doing the same thing, right? Those two are identical tests. You're testing the same idea, right? So that's the what we're talking about, this consistency, right? We're finding, right? So, in other words, if you have only two independent variables, and if you're testing significance of only one independent variable in the presence of, sorry. It doesn't matter how many independent variables you have in your model, right? But if you're running the portions test regarding one independent variable, like this, here, doesn't matter how many independent variables we have, right? Let's say 5. You have 5 independent variables, right? And you want to test whether adding that last variable, 5th variable, makes any difference. Then you don't need this portions test, right? Because you're asking is significance of one independent variable, right? You might as well run t-test. In other words, just look at the printout, computer printout, regression printout, and see whether this one particular variable is significant or not. Just look at the p-value of that one variable, right? That's the same thing, right? So what I'm telling you is you don't need to use a portions test if you are trying to find out significance of one independent variable in the presence of all other independent variables, right? But it is useful in this case. Here we go. Right, here. This is the last slide for today, actually. Okay? And this will be the last topic in the coverage for your midterm exam. Okay? So midterm exam will cover up to this point. Okay? You can test the significance of set of independent variables. Could be 2, 3, 4, whatever, right? For example, let's say, okay, I have model that goes x1, x2, and let's say beta of 3x3, beta k xk, right? And for some reason, you're asking, say, first 3 variables, or maybe last 3 variables, doesn't matter, right? Do these 3 independent variables make any significant difference, right? In the presence of all other independent variables, right? In that case, this portions test is very useful. Okay? You understand what I'm saying, right? So the portions test is typically not used to test only one independent variable, right? But typically it's used to test a set of independent variables, right? And the the test statistic is slightly different. Here we have SSR all minus SSR all except a new set of M variables, right? So we have this, in this case, M is 3, right? So you're asking whether these 3 independent variables are making any significant difference in the presence of all other independent variables, right? Then, so first time you run the regression with everything. Second time you run the regression without those 3 or m independent variables, okay? And then you have to divide it by m. Previously, we didn't divide it by m because what? M was 1, right? We were asking about only one independent variable, right? So still, so exactly the same thing. The F statistic is exactly the same thing as before. We look at the difference between the 2 sum of squares and divide it by the degrees of freedom, number of independent variables in this case. Okay? We're in the set of variables that we are trying to find out, right? And then divide it by MSE for the entire regression, right? And we can test this hypothesis, right? All right? Well, the best way to understand it exactly is doing some practice. Okay? So let's see. In your data, among the data set, there's BB 2011. This is baseball 2011. Okay? This is the post-season time, and that's, looks like both U.S. and Korea are in the heat of this baseball, post-season excitement, okay? And here in the United States, there are 30 Major League Baseball teams, okay? So we have 30 observations here, okay? And we have some statistics. League, Baltimore, Boston, I believe 0 stands for Texas. Okay, so this Texas is American League, isn't it? Let me see. Where's Cleveland? Oh, yeah. So yeah. This 0 stands for American League, and 1 stands for National League, right? So that's just the. We're going to talk about this dummy variable after the midterm exam. Okay? Number of wins, ERA. I believe it's earned run average. Okay? And run score, the hits allowed, walks allowed, and saves and errors. Okay? And let's say you have a model trying to predict number of wins based on all these independent variables. So use the number of wins as the dependent variable, and all the other 6 variables as independent variables. Okay? So we have wins as let's say ERA up to beta 6, it's the last one, errors. Okay? And then, suppose we want to test whether the last 2 variables, let's say saves, okay? Beta, here's beta 5 saves and errors, okay? Whether these 2 independent variables make any significant difference in the entire model in the presence of first 4 variables, okay? Right? Here we have 4 independent variables. We have 2 independent variables, a total of 6 independent variables, okay? Okay, why don't you try that? Why don't you come up with the null and alternative hypothesis first? Okay? And of course, you have to run the regression, right? And that I will get a volunteer to run it on here. Okay? You want to do it? Okay, come over here. Well, hold on. Did you come up with the null and alternative hypothesis? Okay, anybody who comes here and write down the null and alternative hypothesis first, will be able to do that here. Write down the null and alternative hypothesis exactly, and run the test.